Welcome to Brain Vision.
All right, in this problem, we have a car resting on a ramp being held up by a cable, which is inverted is at an angle to the plane of the ramp. So if that's parallel with the plane of the ramp, the dotted line there, we have this one at a 31-degree angle. I'm going to label my block here M. That is my lovely drawn car. And finally, the ramp is inclined at 25 degrees. So in this case, we're asked to draw a free body diagram for the car in part A of this problem. So first, in our free body diagram of the car, let's draw the gravitational force. We always know that is going to be there. And if you are resting on some object, that object is pushing back up on you. So there will be a normal force here extending out. And this normal force will be at an angle of 25 degrees with the axis established by our gravitational force. And then we will have a tension force due to the cable. And if we think of this dotted line as perpendicular to our normal force, then this is at 31 degrees. So the intuitive referencing for me here is sticking along the parallel of the ramp and perpendicular to it. So I'm going to, I'm going to convert both my tension force here and my gravitational force, which is also at 25 degrees with respect to the normal force here. And I'm going to align it along this reference frame. So let's redraw our free body diagram with all of our forces broken down into components. So we have normal force, a small component of the tension force is pointing up here. So that is T sine of 31 degrees. Then the horizontal component is pointed up the ramp, and that is T cosine of 31 degrees. And then the two components of the gravitational force, so pointed in the opposite direction of the normal force, we have mg, and that's the adjacent side here, so that's cosine of 25 degrees. Try that degree again here. And along the angle of the ramp, we have mg sine of 25. So that's our part A. In part B, it asks us to find what is the force of tension in the cable. So we want to solve for T. So if we're looking at our Newton's second law equation, we're given what M is here. I'll write that down, 1130 kilograms. So if we just look at along the plane of the ramp and set up Newton's second law with that, we'll see that our equation only includes terms that we already know and T. So we can use that to solve for what the magnitude of the tension force would have to be in the cable. So we have T sine of 31 degrees. Actually, is the cosine of 31 degrees minus mg sine of 25 degrees is equal to 0. So solving for t leaves us with mg sine of 25 degrees over cosine of 31 degrees. And plugging in our appropriate values for that, I get 5,460 newtons as our answer for part B. In the final part, they ask you to find the magnitude of the force of the ramp pushing up against the car. So we've called that Fn, the normal force here. So let's write out our Newton-second law in the y direction here. So we have Fn plus t sine of 31 degrees minus mg cosine of 25 degrees. And again, it's not moving up and down in the y direction or accelerating, so we'll set the sum of the forces equal to 0. Now we want to solve for the normal force. And once we move over the term with the tension force magnitude in it, we'll also want to substitute in our expression for t down here. So there's an mg that would be in both of these terms once we substitute in t. So when I pull that out, and we would get left inside the parentheses cosine of 25 degrees minus the sine of 31 degrees is divided by cosine of 31 degrees, so that is going to turn into a tangent. So tangent of 31 degrees and times the sine of 25 degrees. And again, we now have an expression where we know all the values, so all we have to do is plug those in and round off appropriately, and I get that the normal force of the ramp pushing back up on the car is 7,220 newtons.